Okay, in this session, let's talk about different types of measurement device and how we assess, how we analyze the performance, including the characteristic of measurement device. So this will be the overview of our discussion in this session. We will briefly discuss few types of measurement device. How do we characterize from static static property, how do we characterize the dynamic properties, and then at the end we will discuss on how we quantify errors in a measurement processes. Okay, let's start it with different types of instrument. In general, we can classify measurement devices into different classes depending on few point of view. The first one, we can classify measurement devices based on the active and passive property, whether it is analog or digital, and whether it is classified as a null type or displacement type. Both these are, we will discuss it in the next few slides. Okay, we can classify measurement devices as a passive or active instruments. This is rather straightforward classification. An instrument is called as a passive if the device does not require external energy for operation. As an example, you can see this classical aneroid barometer, how this aneroid barometer works. So you have a chamber with a certain calibrated pressure inside this chamber. This is a flexible chamber. So if the basically this barometer is meant to measure atmospheric ambient pressure. So if the outside pressure here is larger than the calibrated pressure inside this sealed cell, the pressure outside will press this cell, where this cell is like an accordion system. So if the atmospheric pressure, the outside pressure is compressing cell this cell will be uh, will be compressed, in a sense will be compressed, and then the compression of this cell will change the lever position of this. So if the outside pressure is high, this cell will change the lever position. So the lever position will move, the tip of this lever will move upward, and then it will indicate the pressure scale according to the outside pressure. So there is no external energy needed for this instrument. Same as this sensor, this is a sensor to measure the water level. So if the level of the water is increasing, this will raise up, and then the tip of this lever will indicate the height of the water level. There is no external energy required to operate these devices. What about active? Active instruments requires external power sources. So let's take an example of again a device to measure the height of the water level, same like before. So this float, when the level of the water is increasing, this float will also increase. But then instead of connecting this bar to a scale, we will connect it to a resistance. So when this when this bar is moving up, the length of this resistive element will be getting shorter, and then the shorter the connected length of this resistive element is, the smaller the resistance of in between these 2 points. And then if we connect these 2 points to the uh, uh, energy sources here, power sources, then we will see different current flowing through this circuit depending on the length of the resistive element there. So what it is measured is the water level, but it indirectly measures the water level by measuring the current flowing through this electrical circuit. Okay. Okay. And then there is another point of view to characterize, to classify the measurement device, whether it is analog or digital. Analog device gives an output variable signal that is continuous in time. Okay, what I mean by continuous here, so it's, in a sense, it's not discrete. Between 2 points of value, you can have infinite number of value. Okay, imagine if you are using mercury type thermometer. Hmm? So in between two scales, the mercury level can, well, imagine you are you have very good eyes, and then you look at the thermometer level, mercury level, the scale, using magnifying glasses, let's say. So between two scale, you can see the level of the mercury can vary in continuous way, right? So there is no discrete measurement in that. There is no discrete value in that. While for digital device, the story is a bit different. In digital device, like any system that you have a digital output, let's take a case of speedometer of your car, where the output that you see in the dashboard of your car is it's a digital, just showing a digital number, normally with LCD screen. And then you only have discrete values that you can read there. Between, let's say, 70 kilometer per hour to 71 kilometer per hour, perhaps, you have a discrete reading, 10 discrete reading. So what you can read between 70 kilometer per hour to 71 kilometer per hour, you can only read 70.1, 70.2, 70.3 every 0.1 kilometer increment, let's say. But for analog, you have a continuous difference, continuous increment in the value. Okay, so that is different between analog and digital. And this is the other class of classification, the other type of classification. So this is what we classified based on null or displacement type. So what is different between this? If you have a displacement type instrument, the output of this device will give the quantity of what you measure directly. While for null type, you measure it by comparing it with a reference. So the direct example will be the weight, the body weight that normally we put it in our bedroom. So if you step on it, the dial here will show your body weight directly. While for null type, uh, it works based on a balancing system. So if you want to measure something, you put in one side of the lever and you put reference weight on another side until this lever show a balanced position. In that case, if it is in balance, then you conclude that the matter that you weigh will have the same weight as the reference weight, right? So there is a pros and cons of this. Of course, the most obvious one, if you are using this kind of weighing device, is that for null type it's not affected by gravitational force, right? While for displacement type it's definitely affected by the gravitational force. So in short, then the advantages of null type is that it gives high accuracy. Why? Because what limits its accuracy is only the reference entity, right? The reference of the weight. Easy to calibrate. So mechanically, you don't need a calibration. What you need to calibrate is only the reference entity, right? The reference weight. And less environment dependency. This is exactly what we discussed before. There is no effect of gravitational force there. While the advantage of displacement type is obvious, it's easy to read because you just directly read what it is shown in the output of the device, right? Okay, we have already discussed different classification of measurement devices. Now there are two ways to characterize the property of the instrument: static from static point of view and from dynamic point of view. Let's start it first with static characteristic. So static characteristic, there are many static characteristics that we can quantify, we can assess. These the list of the static characteristic. It includes accuracy, precision, tolerance, range or span, linearity, sensitivity, threshold, resolution, sensitivity to disturbance, and also hysteresis. Okay, so just in order for us to speak in the same language, let's use this terminology. So if we have a measurement device, an instrument here, I or input is the entity that we measure. O or output is the output that is read as an indication of what we measure, right? So let's say if it is about the weighing scale, body weight, body weighing scale. So input is your body weight when you step into the weighing scale. So input is your body weight, you step into the weighing scale, and the output will be the position of the dial that indicates the weight of your body, right? So that is what I meant in here. Whenever I say input, I'm referring to the input of that the entity that we use to that we want to measure, and whenever I say output, that is the output shown by the measurement device. Okay, the first static characteristic that we need to discuss is accuracy. So accuracy is a measure on how close the output reading of the instrument to the actual value. I think this definition is pretty straightforward. Some measurement device might not have a good accuracy, in the sense when you are, let's say again, let's take a weighing scale. When you are measuring 50 kilograms, but your weighing scale shows 53 kilograms. That's not accurate, right? Let's say, let's take a case of pressure gauge. So I have a pressure gauge. The pressure gauge can measure between 0 and 10 bar, but it has an inaccuracy of 1%. So normally accuracy is represented in percentage. What does it mean? If I have that kind of measurement device, that means it can have a maximum error up to 0.1 bar, because the accuracy is represented as a fraction of what we measure. The maximum pressure that it can measure by this pressure gauge is 10 bar. So 10 bar is the maximum reading that we can sense by this gauge. Since the inaccuracy is 1%, which is 0.01, I multiplied by 10 bar, then I will get 0.1 bar. So the inaccuracy can be as far as 0.1 bar. Another statistic characteristic is precision. What is precision? This precision and accuracy, sometimes we mix it up, but precision has a different thing to measure. So precision measure how the spreading of the measurement when we measure a same entity several times. An example again, you have a weighing scale. Let's say your body weight is 60 kilogram. Let's just take a nice figure, 60 kilogram. But when you measure it now, it shows 60.5. When you measure it in a few minutes after that, it gives you 61. And then you measure it again, it gives you 59.8, let's say. And then, so every time you measure it, it gives slightly different result. So there is a variation in your measurement, even though you are measuring the same entity, the same figure, but the output gives variation results. So the precision here gives measure on how the variation of the output of your measurement device when it is measuring the same entity. So this is an illustration of the difference between accuracy and precision. The first figure here, I have a good accuracy, which means this archer, she shoot 5 times. It gives a good accuracy. It is close to the target. The bullseye here, it's close to the target. It's not exactly on the target, but it always shoot at the vicinity of the target. So it's good accuracy. The second example here, the accuracy is not good because it is relatively far from the target, from the bullseye, but the precision is high because she always shoot exactly at the same location, close to the same location after 5 trials. So the precision is high, but the accuracy is bad. So this is best practice, of course, the accuracy is high and the precision is also high. Okay. Okay, there is one more terminology that I want to introduce to you related to accuracy, which is referred to as a bias. If several measurement results give close value, but the result is wrong, then there will be a bias. So same like, let's say the example, I always like to use this weighing scale example. So if your body weight is 60, you measure it 10 times. The first trial you give it gives 61, 61.1, 61.05. It's quite precise. It's quite precise. So it always gives more or less the same results, but it's not exactly, it's not close to the real value, the real weight. Your body weight is 60, but it gives the result around 61. So in that case, your measurement device, your weighing scale, has a bias of around 1 kilogram. There is a slight deviation of 1 kilogram from the targeted measurement. Okay. Another example, when you are measuring your height, but you are wearing a thick soles, so the result is not your height, but your height plus the thick soles, the soles that you wear. So there is a bias which is equal to the thickness of the soles. Okay, so that is the illustration of a bias. The other static characteristic is tolerance. Tolerance, I think we know, you know what tolerance is. It's permissible limit of variation in measured value. So if you have a ruler, let's say, and then yeah, you can let's say the ruler has a scale of one. The smallest scale is 1 millimeter, right? Normal ruler, it has a small scale of 1 millimeter, but sometimes when you are measuring the length of something with this ruler, sometimes you have a reading of let's say if the length is 1 centimeter, sometimes in one occasion you measure the length is 1.05, sometimes it's 1.1, or sometimes is 0.95. So there is a permissible limit around 0.1 millimeter, right? Because of the, probably it's because of the material issue of your ruler. If your ruler is made from metal, when the weather is hot, it will thermally expand, right? So there might be a slight variation when you use the same ruler in different condition, but you still tolerate this variation. This is what we refer to as a tolerance. The next one is span or range. I think this is also pretty straightforward. So if you have a ruler, your ruler, I don't know, your ruler probably the maximum length it can measure is 30 centimeters. So that will be the span of, or the range of your ruler. Okay, the minimum is 0. Of course, you can measure nothing using your ruler, but your 30 centimeter ruler can measure up to 30 centimeter length, right? So the range is 30 centimeter, 0 to 30 centimeter, that says. Okay, the next one is linearity. So what is linearity? Ideally, if you have a measurement device, the indirect measurement device, let's say the simplest example probably is the uh, thermometer, the digital thermometer, right? So the digital thermometer, what it is measured, the input is the temperature of the body that you measure. But if you have digital thermometer, the output basically is the current, which eventually it will be converted to digital reading. But right, so if you have a digital thermometer, actually the output is a current. You see from the display, the digital display, right? You see digital display with LCD screen on it. So what it is, what the output actually is a current. So in this case, there is a relationship between input, the temperature that it is measured, and the output of this thermometer, which is the current. But the current later on in your thermometer is calibrated, so in such what you read in the digital reading is not the current as per se, but it is calibrated to the input entity, the temperature that you measure. But anyhow, the output, actually what you see, the output is the current. So there must be a relationship between input and output. In our case there, the temperature and the current. An ideal measurement device should have a linear relationship between input and output. So this is the temperature, this is the current, and then if you have a linear relationship, then it will be easy. The relationship between output and input is just expressed as a linear function. Output equal to a constant times input plus a. Okay, what is k then? K basically is the calibration factor, is the sensitivity, right? So because what is red is what temperature, what the output is current. If there is a linear relationship, so it is expressed as a linear function like that. K is called as sensitivity, A is the bias. Well, from mathematical point of view, then K basically is the gradient of this line, and A basically is the y-intercept. Okay, this is the ideal measurement device. The relationship between input and output is linear. But in some cases, or in many cases, we don't have this ideal condition. But instead, the relationship between input and output is like this, for instance. There is a non-linear relationship between input and output. Okay, so the relationship is not cannot be presented as a linear function, but it's non-linear. But we don't like it, because if you are doing the measurement, you don't want to be bothered with the relationship between output and input. What we always love in a measurement device is a linear relationship. It's easier to measure, it's easier to manipulate it, and it's easier to be used in control environment, in a closed loop system. So as long as the system is not strongly non-linear, we can always regard it as a linear relationship, as long as this deviation, the nonlinearity from the ideal condition, is not too severe, it's not too much. How do we know if the nonlinearity is too much or not? We have another measure of nonlinearity. So if the blue one is the ideal the ideal condition, the red one, let's say, is the real condition with nonlinearity on it. Now if I plot the difference between the ideal point to the real point here as a function of measured quantity, I will get this plot. So this is the same axis like this, but then what I plot here is just the difference between the ideal point and the real point. If I plot it, I will get something like this. So this red line is not the same as this, but this red line is the difference between blue and red. And then from there we can define measure of the nonlinearity. What is nonlinearity then? Nonlinearity is presented as the maximum discrepancies between the ideal and the real one, which is this one. We call it n hat here. So n hat here is the maximum deviation from the ideal condition, and the nonlinearity is presented as this n hat divided by full scale reading. What is full scale reading? Full scale reading is this height, the span, from maximum output to minimum output. So technically then, if this nonlinearity is small, very small, so the deviation is not that much, that means this red curve is relatively close to the blue line, so we can disregard the nonlinearity, and then we just assume the device as a linear system. Okay, but so the higher the nonlinearity, the higher measurement error that you can expect in your measurement. Okay, let me plot it again here. So Ni here, the one that we plotted, represent the non-linear component of your measurement device. In such, your output, your real output as a function of input, is equal to the ideal relationship, the linear relationship that we discussed before, plus the non-linear components. Yes. So of course then the smaller this one, the closer your measurement device to a linear ideal condition. Three, two, one, action. So let's take a look on this example. Let's say I have a digital thermometer here, where to check the linearity, I record the measurement for its full scale from 0 to 25 centigrade. It seems that this thermometer only has a range of 25 degrees Celsius. So what I did, I calibrated at different value of measurement here, with an increment of 5 centigrade up to the maximum measurement here. So I measure temperature of an entity, of a reference entity, at 0, 5, 10, 15, 20, and 25 centigrade. and then I record the output of my thermometer. Apparently it is 0, 5, 9.8, 14.8, 19.9, and 25 degrees Celsius respectively. And then what I did, I listed down here. So this is the reference temperature, 0, 5, 10, 15, 20, 25, and this is the reading that I get from my thermometer. And then from there I just simply calculate the difference between the output and the input here. So 0, 0, it's 0, 5, 5, I get 0, 9.8 minus 10 is 0.2, and then I calculate till the end, and then I divide it with the full scale range, which is 25. So 0 divided by 25, 0 divided by 25, I get 0. 0.2 divided by 25, I get 0.008. So this column is in percentage: 0.8%, 0.8%, 0.4, and 0.0. This means that the maximum nonlinearity is 0.8. So this is how we define the maximum nonlinearity on the measurement device. Okay, let's take a look again on this graph, this plot, the one that correlate output and input. We discussed it before that this will be the ideal measurement device. The relationship between output and input should be linear as possible, represented by this linear equation where k is the gradient, a is the y-intercept, and k, basically the gradient, is what we call as a sensitivity of the measurement. Okay. Another static characteristic is what we call as a threshold. So what is threshold? Threshold is a minimum level of the measured quantity that can be measured. Imagine now you have a weighing scale. Normally this is kind of weighing scale that you use to weigh your suitcase, right? When you are about to take a flight going for travel, and then you have to make sure that your suitcase is not exceeding the baggage limit of the airline. You want to measure the weight of your suitcase, so you put it on this kind of device. So technically what it measures is the weight of your suitcase, but how it measured, what is the output of this weighing scale? It's basically deflection. So if you look at this weighing scale, it is equipped with a spring with a known stiffness. So when you know the stiffness, you know the deflection, then you can estimate the force. Basically it's just like that, yeah, right? So if this spring, if you know the stiffness of this spring, and if you hang something on it, this spring will expand the length, and then the expansion of the length will be ideally should be linearly proportional to the weight that you attach on this system, right? Why? Because the you know from physics that the stiffness of spring is showing the linear dependencies between force and deflection, right? But sometimes if you don't have a really good weighing scale, there is a friction in here, unnegligible friction in here. So when the suitcase is not that heavy, the friction in here will prevent this spring to expand. And until you attach considerably enough weight to overcome the friction of the weighing scale there. So this is what we refer to as a threshold. So if you attach a light weight on this weighing scale, it will stuck there. It doesn't show any reading, but then at the moment you attach more weight on it, and then it starts to move. So the threshold is the minimum entity that you measure that will produce an output, mainly because of friction in this case. Okay. Next, resolution. What is a resolution? Resolution is the minimum change in the input that can produce observable output value. Simplest example will be your ruler. Typical ruler, it has a smaller scale of 1 millimeter, so the resolution is 1 millimeter. This next one is dead zone. Dead zone is a range of different input values which gives no change in the output value. So sometimes this is related to a threshold also here. Okay? When the input is still too small, when the input is small, then it doesn't give any reading until at a certain input, then and then you can start to see the output. Okay, so this is just an illustration of resolution and dead zone. Let's say we have an ammeter, the device to measure the current, which has a linear scale of 50 division. The full scale reading is 10 m from 0 to 10 m, and half scale division can be read, half scale. What is the resolution of the instrument? So imagine you have 10 m of full scale reading, and then it consists of 10 division. What does it mean? That means the smallest scale that you have will be 10 over 50, 1 over 5, 0 0.2. Okay, 0 0.2 is the smallest scale. But sometimes, if you imagine you have a ruler again, the smallest scale is 1 millimeter, but sometimes you can still estimate if what you measure is if what you measure falls between two scales. So in that case, even though the smaller scale of your ruler is 1 millimeter, sometimes you still can read half millimeter when the entity that you measure, the length falls between two scales. Then you say, oh, this length is 14.5 millimeter, even though the smallest scale is 1 millimeter. So same to this case also, there is a scale. The smallest scale is 0.2 m, 10 m divided by 50, but then you still can read half scale between these two scales, so then the resolution will be half of 0.2 m, which is 0.1 m. And then I have a pyrometer. The dead zone of the pyrometer is 0.125 of the span. The instrument is calibrated from 800 to 1800, so which means the full scale reading will be 1000 in here, right? What temperature change must occur before it can be detected? The full scale reading is 1000, the dead zone is 0.125. That means the 0.125%, that means the real dead zone is 1000 times 0.125, which is 1.25 degree Celsius. Okay. The next one is the sensitivity of to disturbance. We discussed it before. If you have a digital instrument, there might be some disturbance from the environment when the electric current sometimes is deviating because of the environment. There might be a case where you have a thermometer, thermometer, but the temperature of the environment, atmospheric temperature, affect also your temperature reading in your thermometer. That is the disturbance to your sensor. Okay, so this is the good a good measurement device should have less or least sensitivity to disturbance. This because this disturbance can affect the bias in your in the reading of your measurement device. It can also affect the sensitivity. So the first one, it can affect the bias. The A in our linear relationship, O, remember O is equal to K times I plus A, and it can affect the sensitivity, it can affect the K value. Okay, the disturbance can affect this too. So the good measurement device is the one that is least sensitive to the disturbance. So talking more about this sensitivity to disturbance, so we have effect on the zero drift affecting the A in your linear relationship between output and input, and affecting the K, the gradient that correlate output and input. This to explain the one that we just discussed in the previous slide. The next one is hysteresis. What is hysteresis? So we discussed before, we have already discussed nonlinearity. Nonlinear effect is giving a relationship between output and input that is deviating from the ideal linear relationship, right? Hysteresis effect is even worse. The deviation from the ideal linear relationship is different when you are taking increasing measurement and decreasing measurement. So when you are when you are doing increasing measurement, the relationship between output and input is different than if you are doing increasing measurement. So we have double non-linearity here, I can say. Yeah? So how to quantify this hysteresis effect? It's simple. It's pretty similar to what we did in assessing the non-linearity, but now we have to compare directly the non-linearity for increasing measurement and the decreasing measurement. So by definition, hysteresis is defined as the maximum range between the decreasing measurement and increasing measurement. Okay. Okay, we have already discussed about static characteristic. Now we move to dynamic characteristic. Measurement device essentially is a system. Why do I call it a system? Because it is giving an output for any input that we prescribe to it. And measurement device is, strictly speaking, a dynamic system. You have already studied about dynamic system, where In dynamic system, the relationship between input and output is presented by differential equation. So a relationship between input and output is represented by differential equation. As you can see in this equation, you see differential equation in here, where Qi is the input entity, Q0 is the output quantity. So if this is a measurement device, then Qi is the input, the entity that you measure, Q0 is the output that is shown by your device. The relationship between Qi and Q0 is represented by differential equation in here because we have dynamic systems. Okay, so looking at this dynamic system, then we have different order of instruments. If only two coefficients in our differential equation that are non-zero, which are A0 and B0. So let's take a look again the differential equation. So if it is only these and these, that is non-zero, and the rest are zero, so this equation will turn into this. We will have what we call as a zero order instrument. In this case, the relationship between output and input Q0 and Qi is just simply represented by algebraic equation. And technically, here we only have a static system. We don't have dynamic property in our system here. We have static system. This will be the ideal measurement device. But this ideal condition most of the time only happen in our dream. Almost all of the measurement devices are dynamics. We can have first order type. What is first order? First order, if I can go back to the previous two slides, so this one, first order is when only A1, A0 and B0 that are non-zero, or sometimes B1 non-zero is also possible, but only these three or these four that are non-zero, the rest are zero, then we will have a first order instrument. Why do we call it first order? Because it only includes at most the term of the first derivative of output or an input. Okay, so let's take that case when everything here are zero, and then we will have this equation. In particular, here to have a simple illustration, let's just consider B1 equal to 0 as well. Okay, what is the effect of this first order differential equation? If we have this first order differential equation, okay, and then we give a constant input to this system, so Qi is a constant input, I call it U2, U2 is a constant input, or sometimes mathematically we call it as a step input. The input will be like this, it's a step function. Why do we have it step function? Did you say a constant input? Yes, I did constant input, but we give a constant input only from time equal to 0, because at the beginning, if it is weighing scale technically is first order instrument. Previously you don't put the weight on it, but then from the instant you jump to your weighing scale, then you give a constant input to it. Okay, if you give a constant input, this is just a simple differential equation. You can calculate the Q naught easily. Okay, how you do it? Using Laplace transform. I will not discuss about Laplace transform here. You know about Laplace transform, but using Laplace transform you can solve this equation, and this will be the output, right? So this will be the general output based on the boundary condition, the input, the what the parameter of the system itself. You can find the value of capital A and capital B, and then the solution will be something like this. So okay, what does it mean? It means when you are measuring something with a first order instrument, you are measuring something with first order instrument, when the input is like this, the output will show like this, the green one. What does it mean? It means when you measure Qi, the output of your sensor will not immediately show the real entity that you measure, but it takes time to reach the entity that to show the entity that you measure. Okay, the example is what? Thermometer. When you are measuring your body temperature, once you put your thermometer in your armpit, or you are using a infrared thermometer gun, you don't have the result immediately, but you have to wait for a few seconds, because your thermometer needs time to raise the output to the point where it corresponds to the entity that you measure. Okay, that is the behavior of first order instrument. I have already mentioned before, the example will be a thermometer, because thermometer is a first order instrument. So the characteristic of the thermometer, the model, can be represented like this, where T naught is the entity that you measure, the temperature that you measure. T sub T is the output of your temperature, of your thermometer. Okay, so now I have a thermometer. The dynamic characteristic of the thermometer is like this. Tau here is the parameter of your thermometer. T naught is, like I mentioned, T naught is the temperature that you want to measure. T sub T is the output of your thermometer. If this thermometer initially is not a body thermometer, obviously here, if this thermometer initially is resting at 70 degrees Celsius, and then suddenly you use it to measure a 300 degrees Celsius liquid. So you dip this thermometer from 70 degrees to 300 degrees Celsius, and apparently it takes 3 hours to reach 200 Celsius. Before, after some time, the temperature output will reach a point according to the entity that you measure. After some time, it will reach the point correspond to 300 degrees Celsius. But it takes 3 seconds to reach to 200 degrees Celsius from 70 degrees Celsius. And then there comes a question, when this thermometer will give a reading of about 1% away from the actual reading from 300 degrees Celsius. How long do I have to wait to get that reading? So this can be calculated using first order differential problem here. let's do it together now. So okay, this is the model of the mercury glass thermometer. Yeah. It is represented as a first order differential equation where T naught is the input, the quantity, the temperature, the entity where the where its temperature you are going to measure with this thermometer, and T sub T is the output of this thermometer. Tau here is the parameter of your mercury glass thermometer. Okay, so we are going to solve this differential equation. How I'm going to do it, that I will use Laplace transformation to solve differential equation. So if this function t sub t, this function in differential equation, of course, all of these functions are in time domain. So t sub t in here is a technically is a function in time domain. Sorry, it's in time domain technically, right? We are going to transform it to Laplace domain now. So if you transform a time domain function to Laplace domain, then it will become a function of t sub t in Laplace domain. No, right? So this is the function of t of your thermometer in Laplace domain. And now what I'm going to do, I will Laplace the first term. Tau is constant, so it doesn't change anything in Laplace transformation. But the first derivative of t sub t here, when we Laplace it, if you refer to Laplace transformation property, you know about this. This will be equal to s times Laplace variable times the function t sub t in Laplace domain plus, sorry, minus t of t function of time when time is equal to 0. Okay, and then we have to do it all for the right hand side. T naught is a constant, is your input here. 300 is the input of your to your thermometer. So T naught basically is a constant in Laplace transformation. If you have a value of 1 in time domain, 1 when you transform it to Laplace, it becomes 1 over s, right? So T naught basically is T naught times 1. So T naught, when you transform it to Laplace domain, this will become T naught over s, right? So now I will group the T sub T with other T sub T, and then I will group the rest. So this will become tau s plus 1 times T sub T of s, right? Equal to T naught over s plus tau times T sub T when time equals 0. And we know it from here that T sub T when time is equal to 0 is equal to 70. So I can rewrite this equation now to become tau s plus 1 equal to I will just manipulate mathematically this equation. This will become 70 tau s plus t naught over s, right? And then I will analyze it for the function itself, t sub ts. This will become 70 tau s plus t naught over s tau s plus 1. And then to make my life simple, I will just divide both side numerator and denominator with tau. So this will become 70s plus t naught over tau divided by s plus 1 over tau. And then what next? I will just simply do the partial fraction expansion because I have two factors here in the denominator s and s plus 1 over tau. I will change this form into something that looks like this. Okay, and then when you evaluate a and b here, you at the end you can do it by yourself. I will not do it here. At the end, you can find that a will be equal to t naught, and b will be equal to 70 minus t naught over s plus 1 over t. S plus 1 over t, yes. So once you have this form, you can just simply refer to the Laplace table, and then you can find the t sub t in time domain. This will be just simply the inverse Laplace of this function, the function in Laplace domain. And then again, if you refer again to Laplace table, you can immediately find that the inverse of it, the inverse of t naught over s, 1 over s is a unity is 1, so t naught over s, if you inverse Laplace it becomes t naught, right? And the second term, please refer to your Laplace transformation, will be equal to exponential of minus t over tau. Okay, now let me rewrite it to make it nicer. This will be equal to t naught 1 minus exponential of this plus 70. So this is the result. We still don't know what tau is, right? This tau, sorry, not that one, I circle wrong. This tau, we still don't know this tau. We need to find this tau, but how to find it? It's easy because you know the boundary conditions here. So how to find the tau? You can just simply use this value and then substitute it to this function. You know that when time is equal to, so when this time is equal to 3, when this time is equal to 3, then this value will be equal to 200. So you just substitute it there, then you can find the value of tau. And then to answer the question, at this point, let's assume you have already known the value of tau, and then the question asks you to find when will you reach the result within 1% of the final value. If you look at this function, again, the plot of this function will be something like this. So this is the temperature, this is the time. The plot of this function will be something like this. It will exponentially increasing, where the initial value is 70. So when t when t is 0, the temperature will be 70. But then when t approaches infinity, then the temperature will be equal to 300. That means this value is 300. So to answer the question, when will it reach 1% or 1% of the final value, 1% of 1% from 300, that means 1% of 300 is 3. So 1% away from 300, that means it is when the value is 297, right? 297 is 1% away from 300. So the function of this t sub t. What is asked by the question is this time value. So how to do that? Again, same like before. You just substitute the value of t of the time that you are looking for. This should be equal to 297, and then using this function, the function that you have evaluated, the function where you have already know the value of tau, you can find the time. So this time is the time that is asked by the question. I leave it to you on how to find the value, but step by step wise, everything has been discussed here. Okay, let's go back to the slide then now. Okay, we have discussed previously first order instrument, but zero order, first order is not all of them. We might also have second order instruments. So it's quite analogous to the first order instrument. Second order instruments here means the differential equation that correlate input and output involves also the second derivative of the output. It can be also with the input, but for simplicity, let's just consider again like before, b1 0, also b2 is also 0, or non-zero coefficient that we have is only b0, k0, a1 and a2, b0, a0, a1 and a2. So we have 4 parameters now. If I simplify this equation by introducing these 3 parameters, k, omega square, and eta here, then I can rewrite this differential equation, okay, with a new form. And then if I present it in the Laplace domain, it will be something like this. I leave it to you to derive this Laplace domain equation. Now, I think you know about this. This basically is similar to the theory of vibration. If your eta in the vibration, this corresponds to the damping value. If this eta is greater than 1, then you will have non-oscillatory response. If eta is equal to 1, then your output is still non-oscillatory. But if eta is less than 1, between 0 and 1, you will have oscillatory response, because this eta basically is similar to a damping ratio. So if you need to refresh your memory, you can pause this video here, refer to your vibration course when it is talking about second order system, and then you will refresh your memory again about this. Okay, but this second order system applies also to some types of measurement devices. Okay, and then typical second order measurement device will have eta or damping ratio between 0.2 and 0.6 for a certain reason. Why? Because when your damping ratio is between 0.6 and 0.8, the rise time will be reasonably fast. But if it is too low, you will have large oscillatory, which you don't like it, of course. But if the eta is too high, close to 1, then the response will be too slow. You don't like it also. So typically, when we have second order measurement device, the damping ratio, the eta value will be between 0.6 to 0.8. The next topic that I want to discuss is about quantifying errors, but I think I will do this in the next video. Okay.